Swayam Prabha. Digital India. Educated India.
So, in this class, let us review the subject that we have learned so far. And in the first chapter, we discussed the force systems. We have looked at a concurrent force, which is also seen in trusses. And we discussed in practice, all forces are actually distributed. When I have a pin and a hole contact, we replace it by a concentrated force, and if you really look at what happens, you have a distribution. Rigid body is an idealization, concentrated force is also an idealization, goes hand in hand with rigid body idealization. Then we have also looked at body force you have from rotating platform like this. And another important concept is we have to quantify what is the rotating effect of the force. We understood what is the meaning of a bending moment and so on and so forth. And one of the important concepts that we understood in the process was transmissibility of force. When we are looking at the external effects, it is independent of the point of application of the force along its line of action. And if I make the boat smart, with this force, it will move forward. Suppose I move the force to the back and then make the boat smart, it will also move forward. So, the external effect does not change, and what you understand is pulling or pushing is producing the same effect on the body under consideration. Suppose I look at what happens when I apply two forces like this. This is applying a tension. A rigid body by definition will not have any change. If the body is deformable, it would get elongated. If the body has a compressive force, it would get compressed. And what we learnt was, even though the internal effect is different, the shape of a rigid body will not change by definition. It makes our life fairly simple at the initial stages of the course. We have also learned force is a sliding vector, slides along the line of action. And particularly, this is useful when you have to reduce a given force system into its resultant, or when I have multiple forces acting on it. If I have to find out the resultant, you use the principle of transmissibility to simplify the force system and find out the resultant comfortably. Then the important concept that we learnt was, what is the meaning of resolution of a force into a force and a couple? I take point P1 and I have a force F acting on it. I can freely move this along its line of action. Suppose I want to find out what is the effect of the force acting at point P1 to point P2. I cannot simply move the force to point P2. Suppose I want to maintain the external effect as same, I can add another force and subtract here. I have put this force here and I have subtracted this force here. This is similar to what is the situation here. Since we have learnt what is the meaning of a couple force system, we could visualize the force here and this force here would form a couple, and you have the perpendicular distance as d. So, I can visualize sliding a force from this point P1 to P2. It actually amounts to, in addition to a force, you also have a moment. and we found that this is a free vector. I can slide the force along its line of action. It is fairly simple, but if I have to move the force from point P1 to P2, if I have to maintain the external effect, I have to have a force as well as a couple. And this is what we said finds repeated applications in the study of mechanics, and I have also advised that you should master this technique, and you can also reverse the above procedure. If I have a couple and a force, I could find a force acting at some arbitrary point, which we will have to find out the location. And we understood the subtleties between a moment and a couple by taking this example. I have a force acting on this handle. Now, I want to find out what is the effect of this force on this shaft. The free body diagram is shown here. Let us go in stages. I have the force acting at this point at a distance b away from the plane on which I want to find out its effect. I would move this force horizontally like this. We know I cannot move this force horizontally unless I have a couple. Fine. So, this would result a couple which is given here, which will be F into B. Then I would move this force from this level to the level of the x axis. So, I have this force when it is moved. What I will have is, I would have a force acting on it as well as a twisting moment. My ultimate interest is to rotate the shaft, but if I apply the force with one pin like this, it would introduce a force as well as an additional moment Fb. On the other hand, if I put a equal and opposite force system, it would only produce a twisting moment on the shaft. So, this brings out a subtle difference between rotating the shaft with one handle, rotating the shaft with two pins attached to the handle. Fine. So, we have a necessary foundation, and one of the common doubt the students had was, you had shown a beam and there is a welded arm like this. I have a force P acting on it. And when we discussed in the class, we replace the force which is acting at a distance on an extended arm as a force and a couple acting at point B. This comes out naturally if you look at how do you apply the principles that you have learned. But the doubt was, you said the force is following a principle of transmissibility. Why not I simply move the force and find out the bending moment acting on the beam? Why not I do that? It is because you have not understood the concept very clearly, and I would counter it by another example. See, in this case, when I move this force, the member is still there, and then you are able to have the force hitting on the member. The member as such does not feel the force like this, it is feeling only at the point of weld. That is where the confusion is. Suppose I have another problem where I attach a bar like this and I weld it here, I apply the force here. Now, let me use your argument of transmissibility. I have this is the line of action, and then the force is moved along the line of action. It is not touching the body of the beam anywhere, like in the previous example. When I have a force system like this, you would naturally feel I cannot move the force like this and then try to find out what is the effect on the body. You would only see that this is the arm attached to this body, and you would naturally reduce this as a couple acting like this. You have to look at, yes, principle of transmissibility tells pushing or pulling has no difference, but you cannot apply it randomly. When I have a beam, when I have an extended arm where I put the load, the beam senses that force only at the point where it is attached. So, you have to apply the principle properly when you want to understand what is the force system that is happening on the beam. Is the idea clear? This is one of the doubts that students have raised. Why not I simply transmit the force? See, once I put here, this will be a force which can go in the line of action. That is fine for resolution or simplification, you can do that. But the beam as such does not feel this force the way that you want to translate and then look at it. It feels this force as a moment acting at this point. The same argument is valid for the previous example also. Now, we move on to solving a simple problem in 3 dimensions. My idea is, I have deliberately focused on 2 dimensions. I said at this level of the course, you have to visualize what happens, and visualization is far simpler when you are handling 2-dimensional problems. I would like you to visualize whether the bending moment is acting in the clockwise direction or anti-clockwise direction. That training has to come, which can come when you solve 2-dimensional problem. It is easy to scale up to 3 dimension. It is not a big deal at all. Fine. And this is also a problem given in your assignment sheet. So, you have a transmitting tower and you have this supported by 3 guy wires, and the problem also specifies what should be the selection of the coordinate system. Fine. And when I have to do a problem like this, I have to first identify the coordinates of the key points. I have point A, and then I have point B, I have point C. That comes from your geometry. Then you have to have the coordinate of point D. Then I have these guy wires are cut and they would essentially transmit tension. We also label them as FA, FB and FC. And the first and foremost step is, I need to find out the unit vector along these forces. Fine. And for me to write the unit vector, it is easier if I write the coordinates first, and I take, if I have to find out the unit vector from D to A, so final minus initial divided by the distance, that gives me the unit vector like this. And similarly, I will have to do for FB and FC. So, there is no big deal. I mean, you have to do little more mathematics. So, that is the reason why I said that let us not focus on 3-dimensional problems. Concepts can be better understood when you solve 2-dimensional problem, and you will also be forced to visualize. That visualization is very important for engineering. Fine. So, I get the unit vectors along these directions, and then you have a simple mathematics. I have to find out what is the tensile force acting on the guy wire. I get this value because it is given in the problem what is the tension in A, and I have the unit vector. So, similarly, I can find out what is the force acting on guy wire B. I can also find out the force acting on guy wire C. It is all fairly straightforward. You have a little bit of arithmetic involved. Other than that, the procedure is very, very simple. Then I find the net force. This is FA plus FB plus FC. I get this quantity like this. Then I have the moment, I simply put it as R cross F. You have already learnt R cross F, and it is very difficult to visualize in a problem like this, and your R cross F will automatically give you the necessary result that you are looking for. So, I finally get this as 4024 I minus 6971 J kilonewton meter. So, scaling F from 2 dimension to 3 dimension is fairly simple. You have all the fundamentals that you have that are required to solve such problems. The only requirement is you have to apply them systematically. You have to be patient in identifying the coordinates and find out the unit vectors properly and then do the arithmetic. Then we have also looked at, in many systems you could identify equilibrium very easily if you recognize that I have a 2 force member or a 3 force member. And the question raised here is, if you have to keep a body in equilibrium, you need at least 2 forces. And how these forces should be? They should be collinear and equal and opposite. You would use this property when you recognize in an assembly of rigid bodies, if there is a 2 force member, you use this information effectively to reduce the complexity of the problem. We have done the problem of a crimping tool. Initially, it was looking as if it is too difficult problem to solve. Once we split it up as links and identified 2 force members, the problem was very, very simple. 2 force and 3 force member assembly is what you come across in many problems. It is a very important clue. And we have also looked at what way you will do when you have the 3 force member. I have one situation where the force is not balanced, so it will have a translation. In the other case, the force polygon is closed, but it has a net moment, and the way that you can visualize is the third force has to pass through the point where the other 2 forces meet. And we have also discussed, if I have to have a necessary and sufficient condition for equilibrium, I have to look at for every conceivable subsystem. And we have also looked at different types of supports. I have a roller support, I have this bearing, so on and so forth. Okay. Then the question is, yes, when we had discussed the necessary and sufficient condition, in that chapter I took up 3 example problems. I did solve for the system as a whole, and for some sub-assemblies we verified whether the f equal to 0, m equal to 0 is satisfied. Have we done that for all other problems we have discussed later? If you go back and look at, when you looked at the truss problem by the method of joints, in fact we did that. We have taken a joint A, isolated the joint, and we have also put the forces to start with as away from the joint. Then I had used the arithmetic and found out what is the actual force, reverse the direction. Then I moved to the joint F. And I put these forces properly, and my arithmetic gives me what should be the correct direction of F, Fe and so on. So, what we did was, we isolated this subassembly, isolated this subassembly. At least in the method of joints, even without your knowledge, you had verified the equilibrium condition for every conceivable subsystem. In the method of sections, when you take a section, you should analyze the left free body as well as the right free body, which we have not done. Where does error that precipitates when I do not follow this? There is one nice example I said in the case of in the Crandall and Dahl, the first chapter, he has given a nice problem. I wanted you to do the reading assignment, and this is a universal joint. If you look at a truck, at the bottom of the truck you will have this. From the engine you will have the rear wheels are driven through this universal joint. It is very prominently seen in trucks. You have a look at it. You learn engineering only when you look at systems around you. So, you need to transmit torque from one axis to another axis. A simplified model was taken up in Crandall and Dahl, and they have analyzed it. And what they did was, they have taken the bearings to start with as thin bearings. When you have the bearing as thin, suppose I have the load, This is also slightly thick. I should have had just half of it. And when I apply a force, it will just come down, and I could replace the role of a bearing simply as a single concentrated force. So, if you do this kind of an assumption, the problem is initially solved. You have reactions at the bearing, a single reaction in this plane, single reaction in the other plane, and they have analyzed the system as a whole and got an expression relating the torque MA and MB, and the result was their equal torque. Then he goes about and dismembers the subassemblies, and he finds equilibrium condition is not satisfied in a subassembly. Then he raises a question, what has gone wrong in the process? Because when I say the system is under equilibrium, it should satisfy for the system as a whole as well as all the subassemblies. When he does that exercise, he brings in an important factor. We have considered the bearings as thin. If it is a thick bearing, when I have a force, it will have a situation like this. It will be inclined and it will make contact at 2 points. This happens on the vertical plane, this happens on the horizontal plane. When I show it for 2 different planes, you can visualize it for any other plane. So, replacing the bearing reaction as single vertical force is not going to solve. And when I have a 2 force, it is also going to transmit a moment. So, the mathematics has helped in improving the idealization. So, this is where the mathematics helps. Okay. And when they do this analysis, the bearing is no longer can be idealized as a thin bearing, it should be idealized only as a thick bearing. And when you translate it in the free body diagram, I would have 2 forces acting on the at the place of the bearing. And when you do this, subsystems as well as the system as a whole remain in equilibrium. And you get altogether a different answer. The torque here is MA cos theta for this particular configuration. For another configuration, the expression would change. So, the focus here is as long as your idealizations are clean and neat, and that reflects the physics of the problem, when you find out the condition satisfied for the system as a whole, subsystems also will satisfy. Because the problem dealing with the truss or beam are so simple, you idealize the supports, these idealizations are reasonably good, even though we have not specifically insisted on analyzing the subassemblies, the answers were correct. So, the message here is compare the predictions with the behavior in the actual system by an experiment. It is not that you say that I will idealize like this and solve the problem. What for you are idealizing it? You are trying to understand what is the actual problem that you have, how well you have understood, and how to verify whether your modeling is correct. Ultimate goal is it has to satisfy an experimental result. Fine. If satisfactory results are not achieved, reconsider the steps of analysis. A frequent difficulty is a failure to select an appropriate system or systems to define actions on it by its surroundings. So, there could be a problem in what you identify as a system. This is one type of problem that you may encounter. It may be necessary to alter the assumptions regarding the characteristics of the system. This can lead to different idealized model of the system. This is what we had seen in the nice example of universal joint. See, it is also difficult to coin simple problems to illustrate concepts. You should at least appreciate the team that they coined this problem and then figured out that mathematics ultimately helps. See, we have all along said, and if you are not dealing with problems involving friction, I can assume the reactions in any direction, unknown forces in any direction. My mathematics will tell me what is the correct direction. And here you have an example, if I verify the necessary and sufficient conditions, it also helps you to verify whether the idealizations you have chosen to solve the problem are indeed appropriate. Fine. And you have to know, I said whether some of you have had an experience of river rafting. You see the ship is going in the sea. What is the kind of forces that happen on this? Just have a look at it. It is caught in a storm. And so, one of the most difficult aspect in any engineering is how to identify the forces acting on your system. Do not think that whatever you have studied in this course is great enough for you to feel proud of. You have to keep in mind that we are taking baby steps. We are learning idealized systems and idealized force interaction which somebody has given you, and whole of engineering lies in how to identify the forces that act on your system for you to analyze. Look at the wave, it goes through the complete body of the ship and it should be about 20 to 30 feet high. And your system has to survive, it cannot collapse. So, have humility, that is very, very important. Then we moved on to discussing about trusses, and we emphasize that no member is continuous at a joint. You have a gusset plate, whether it is a 2-dimensional problem or a 3-dimensional truss. I have idealized for a 2-dimensional case as a pin joint. For a 3-dimensional case, it is idealized as a ball and socket joint here. And we have also seen that loads are applied only at the joints. That is a very important aspect of it. And we also learned two methods. One is a method of joints. I take out a section like this and then I analyze this. And I can also take out a section like this and then you call it as a method of sections. In the case of method of joints, it is a concurrent force system. So, I can write only two independent equations. In the case of method of sections, I can have non-concurrent force system and I can do 3 equations. And we have also discussed how to associate the member force as tension or compression. And we discussed at length, when I have a pin at a highly magnified perspective, you will have a clearance, and if you assume that the member is under tension, the force interaction has to happen here and here, so that this member is under tension. But if you analyze the pin, you would naturally put the force like this. And I said engineering is one profession where you use convention. If you use this kind of an approach, then I should put this force interaction only on this direction, indicate the force at the pin on the same side of the member. Then you can interpret, if I have a force away from the pin, you call it as tension, and if it is towards the pin, you call it as compression. Okay. Force away from the pin is indicating tension, force towards the member is indicating compression. All that circus is much simpler if you follow our discussion of isolating a joint along with the member. It is easy to visualize when you put the force away from the member. It is easy to perceive that it is tension, and I have also discussed our mathematics is such, when I get negative, it automatically becomes a compressive force. We have taken advantage of the choice of unknown force direction to start with. And in the case of method of sections, we had taken a section with 4 unknowns, but we could still solve it. I can also do the same trick if I have method of joints. Suppose I have unknowns FAC, FAD and FAB. In this case, FAC and FAB are along the same line of action. You choose a coordinate system along this line of action. Even though I have 3 unknowns at the joint, I can find out the third unknown if my interest is only on FAD. See, the basic requirement is if I use method of joints, find out a joint which has only two unknowns. If I use method of sections, cut a section which has three unknowns. We have seen exceptional cases in the case of method of sections. Method of joint also, I can do the trick by identifying a suitable coordinate system. So, it is better that you learn many methods that you have. And I said that we have focused mainly on two dimensional trusses. Suppose I go for a space truss like this, what is the difference it is going to be? It is all supported by ball and socket joint, and you will have to go back to your vector algebra and solve the problem. Without vector algebra, it is difficult to handle a problem like this, and you have three reactions at each one of these supports, and they are handled in a similar fashion. And we can also look at whether the problem is statically determinate or not. The main difference is, instead of m plus r equal to 2j, I would replace it by 3j, because at each support when I have a ball and socket joint, I can write three independent equations. That is the only difference. Rest of it becomes vector algebra for you to do it, and you lose out on visualizing what happens physically. And here again I can use this is a statically determinate problem, because I have number of joints as 5, number of members as 6 and reaction as 9. So, I can solve this problem with m plus r equal to 3j. And when I do this, I have to find out the unit vectors. After I find out the unit vectors, isolate a joint like this, and then again you do the forces like this. And since I have vector as ijk, I can solve for three unknowns. So, equating the terms I, j and k. Here again you can find out the member forces, associate whether it is tension or compression, so on and so forth. So, scaling up from 2 dimension and to 3 dimension is not at all difficult. That is what I am trying to say. It is only little bit involvement in mathematics, but while learning the subject, learn it thoroughly for 2 dimensional system. You can easily graduate to 3 dimensional system. I have all these forces where the direction is also modified and so on. Then we moved on to discussing beams. We have understood any member that supports transverse load, we call it as a beam, and we discussed that I should have the loading diagram, shear force and bending moment diagram one below the other. And in this chapter also we have discussed about sign convention. It is a discipline, because depending on the problem complexity, you may want to analyze the left side of the beam or the right side of the beam, and I should follow one single convention, so that whatever the result I get from analyzing the left portion or the right portion, it is unique in magnitude as well as sign for me to plot shear force and bending moment diagram. Magnitude may be same, but the sign may become different. So, it is more of a discipline. Okay. And what is a sign convention? We have to identify this as a positive surface, and then we have to identify this as a negative surface. Since we have adopted Merriam, we will use that sign convention. On a positive face, positive moment is positive and negative shear is positive. This is what you have in the case of Merriam. I take the moment anticlockwise and shear force downwards. This is to draw the isolated section. Once I draw the isolated section, all my signs I have to refer it with respect to the reference axis. Okay. You should treat this force as negative when you do the force balance. You should not miss that. On a negative phase, negative moment is positive and positive shear is positive. And we have also looked at the concept of what I have said is you take a section and then do it. I expect you to do this in your examination. So, find out suitable planning of your answer script, so that you do all this calculation separately and reserve a space for you to draw the bending moment and shear force diagram one below the other. We have these expressions, you have seen it earlier. I have drawn the bending moment and shear force diagram one below the other. I have these expressions. And in this context, I also discuss all systems in practice are in some way non-linear. We idealize that as linear system. Why do we do it? We do this primarily because I can exploit a principle called principle of superposition. I can rethink that this problem is consisting of two different loads, load P and load PB. I can get the shear force and bending moment diagram for the load P. I can get the shear force and bending moment diagram for the moment. I can simply add this, I would get this answer. This problem is very simple, I just brought it for illustration, and this is a very powerful principle that will be used in your later courses. Not only this, when I have a slender member, it can in principle transmit 3 forces and 3 moments, and we have seen bending moment in the plane xy. We have looked at bending moment as mxz. Suppose you have a member which is transmitting force in one direction, also transmitting force in a direction perpendicular to that. You can apply principle of superposition, draw the bending moment diagram for this loading, draw the bending moment for the other loading. So, the principle of superposition can be exploited for this also. Even though we have not solved any problem, you can also handle such situations. Then we looked at when I have a variable load acting on the beam, we developed the interrelationships. We realized that we have made a deliberate cut at a section of delta x, it has a length of delta x. So, I have to recognize that there will be variation in shear as well as variation in bending moment, and when I use this, we have got the final interrelationships that relates what is dV by dx and what is dm by dx. And we have also discussed how you can exploit these expressions to correctly draw your shear force and bending moment diagram. Okay. And I have asked all of you to solve this problem. It is no big deal to make your problem involved in calculation by putting several forces. We have solved series of simple problems. It is no difficulty at all to handle a problem like this, and I think I have also given you the reactions and the supports, so that there is no difficulty in comparison of your answers. For me to find out the reaction, I can replace this distributed force as a concentrated force, and all of you have determined the shear force and bending moment diagram by taking appropriate sections, drawn the free body. Now, I am going to discuss a method to verify it. Use this for verification. For all your problems in quizzes and exams, you have to take a section, show the free body, write f equal to 0, m equal to 0, find out the unknown forces. But once I have obtained all this, how do I verify it? See, for me to plot the shear force, I move from left to right with the Merriam convention. When I start, I have this Wx, x is 0. So, I have this as 0, I start at 0, and this is uniformly distributed. So, from section 1 to section 2, it has to be a linearly varying shear force, and I find out what is the shear force at section 2. I mark this point, and I would join these two by a straight line. Then at section 2, I have a shear force, that is the support I have. I can find out what happens at section 3, the value. I can mark them like this. I should not join this to this point. I should recognize at this point I have a shear force. I would join a vertical line like this. then it remains constant till 3. Fine. So, if you do like this, I will come down. When I have the force like this, I will come down. That is how the calculations will be. Okay. And then it will remain constant. The moment has no role to play in the shear force. Then I will come down by 12 kilonewtons. Then I will go up by 2.84 kilonewtons. So, the plot will start from the left to right. You can trace the forces. So, the key points are wherever you have external force, they serve as key points. And you should also decide how many sections you need to take to solve this problem. And let us go and draw the bending moment diagram. For bending moment diagram, move from right to left. Simply find out whether it is clockwise or anti-clockwise moment and then keep plotting it. That is all you have to do. For the first one, I have translated the force and indicated that I need to get a moment like this. Okay. And I have got this value here. And many students have asked me the question, how do I handle a concentrated moment acting on the beam? Very similar to how you handle the force acting when you plotted the shear force. So, when I go here, I should recognize that there is a step increase in the bending moment. Fine. I should recognize that there is a step increase at this point, and if you recognize that, then it is very simple to do. And wherever you have load, you have a change in the moment diagram. They are all key points. When shear crosses 0, you have extremum values, and you can figure out, because I have the slope is 0 here, I can figure out this, or even otherwise I can draw a straight line and find out what is the average. If my equation gives more or less, I can find out what should be the curvature of this. Okay. Then we moved on to position of equilibrium. Okay, there we said that we need to focus on active force diagram. We also discussed concept of degree of freedom. I have a single degree freedom system. I have multiple degree freedom system, and I have 2 links. And in all these cases, you need to plot the displaced position, and you have a nice animation of lift like this, which can be deployed quickly. And let us solve one very interesting problem by force method as well as virtual work. Okay. And this kind of a press you will come across normally in many industries. I have a handle like this, and somebody pulls this down, then it presses this object here. And it is a pin joint here. It is also a pin joint at D. It is also a pin joint at C. Suppose I have to find out what is the reaction at A. By the force method, I have to dismember all of these members. Then only I can find out the force. We would solve by both the methods, and you will find virtual work 2-3 steps you get the final answer, whereas a force method requires computation, and also in the process you learn how to find out reaction by the method of virtual work. You have to replace it by an active force, which we have learned by looking at stability. We have replaced a spring by the restoring force. And when you are solving by the force method, I expect all of you to write in all the problems idealizations. So, what are the idealizations you have? Joints C, D and E are pin joints. A acts like a roller. Part B moves smoothly over the column. We are avoiding friction. Okay, that makes our life simple. And you have the geometry which is shown as a line sketch, which is useful for the method of virtual work. And I can also visualize when I pull this, what would happen to the link. So, in the case of method of virtual work, I have to draw the active force diagram, which is mentioned here. I have to find out the reaction here. So, I just put the reaction by an active force, and when I pull this, this will also move. If I do not consider that this moves, I will not be in a position to solve the problem. So, first let us solve this as a by force method. The problem looks complicated, it is not complicated at all if you recognize a few important things. So, you have the member DEG is one unit, okay, it is a one physical member, and when I have a pin joint, I can replace the interaction at the pin joint as two forces, we do not know the direction, and I have assumed a direction like this on this. This is connected to the link DC. So, I have to put the link DC and then put these forces opposite to this by Newton's third law, and you should recognize that link DC is a two force member. The moment you recognize this as a two force member, the force has to be along its line of action, okay. That makes your life fairly simple. So, once you determine the force RD, I can put this RD here. For me to write, my interest is to find out in this what is the reaction here. So, if you look at here, I need to find out the vertical component of D, force at D would be identical to this. So, I would replace this. These are all simple mathematical simplification. I have RDY as tan 15 RDX from the given problem geometry. Then I go to the next step, I put only essential things here, take moment about E, I get the value like this, this gives me RDY equal to 966 newtons. I get RDX as 259 newtons. So, I have dismembered this, determined the forces here, then I have to find out the force. This force I can easily find out because I have RDY. Then I have to identify what happens the interaction of C with respect to this bottom block. That is what I have listed it here. So, you need to have reference axis. This is again a pin joint, can be replaced by two forces, and you will have a reaction from the pole that is put as a normal force, because I have a smooth movement upward and downward, there is no friction. And this is a roller with a flat edge, and this is also smooth. So, I have a reaction R. So, this clearly shows I have R equal to RCY equal to RDY. So, the question asked is what is the reaction force? We have got the reaction as 966 Newton. Circuitous process, I have to dismember and do it. This is what is asked, but we will also see what are the forces acting on this member. Can you recognize what is this member? How many forces acting on this member? You should recognize that this is nothing but a 3-force member. See, many mechanical appliances, you can see them as assembly of 2-force and 3-force members. I have a force acting on this, which is what the operator is pulling it down. Then you have the interaction at D. You can easily say what should be interaction at C. I have these forces meet at a point, and it automatically says the force acting at E has to follow this line of action. So, this also gives you the force RE excess 311 newtons and RUY equal to minus 773 newtons. This is just to appreciate seemingly practical problem can be thought of as assembly of 2-force and 3-force members. Now, we move on to method of virtual work and simply solve it in no time. Okay. You see the power of virtual work. I have delta W equal to 0. I have the geometry, and we have to identify the reaction. So, make that as a active force, and you have to look at what is the work component of this. Here the force and displacement are opposite direction. So, I have negative, Here force and displacement are same direction, so I put this as positive, because this is the sign convention we discussed. Don't individually assign a sign for the force or the displacement. Look at the work component, okay. Look at the product and then assign the sign, and this gives me in one step I get R equal to 966 Newton. So, this brings out the elegance of method of virtual work. Nevertheless, you will also have to know how to solve it by the force method. I thought it is a nice problem where I can review, because it is a class on review. I could bring in how we have solved it by the force method, how we can solve the same problem by method of virtual work. I suppose we had a fairly good discussion on all the key concepts, including the sign convention used in trusses, beams and virtual work. Thank you.